Hey everyone, and welcome. Today, we're going to take a visual tour of a really cool concept, symmetry. It's one of those fundamental ideas you see in geometry, in art, even in nature. And trust me, by the end of this, you are going to see it everywhere. Okay, let's get into it. So just take a look at this amazing bridge. What is it that makes it so, I don't know, so satisfying to look at? Well, a huge part of it is symmetry. See how the left side is a perfect mirror image of the right? That creates this incredible sense of balance and harmony, something our brains are just naturally drawn to. And it's not just in stuff we built, it's a basic principle of the natural world, too. Which, brings us to a great question. What do a bridge, a butterfly, and a snowflake actually have in common? Well, you guessed it. They all share this beautiful property of symmetry. And today, we're going to dig into the geometric rules that make it all tick. First up, let's talk about the most common type of symmetry you'll probably run into, line symmetry. The easiest way to think about it is like a perfect mirror image, where one half of an object is an exact reflection of the other. Okay, let's use this rectangle ABCD as our example. That vertical line running right down the middle, we'll call it line L. That's our axis of symmetry. Now, what that means is for any point you pick on the left side, say point X, you're going to find its perfect partner, point Y, on the right side. It's an exact mirror image across that line. So here's the formal definition. I know it sounds a little technical, but we literally just saw it in action. It says line L has to be the perpendicular bisector of the line connecting X and Y. That's a fancy way of saying two really simple things. One, the line from X to Y hits our symmetry line at a perfect 90-degree angle. And two, the symmetry line slices that connecting line exactly in half. That's it. Okay, so we've got the vertical line of symmetry down. But what do you think? Does this rectangle have another one? Take a look. Is there any other line we could draw that would act as a perfect mirror? And if you were thinking of a horizontal line, you nailed it. Absolutely. This just goes to show you that a figure can definitely have more than one line of symmetry. Here, we've got this new line M running straight through the middle horizontally. And here's why it works. It's the same exact principle as before. Our new line, M, is the perpendicular bisector, but this time for points that are stacked vertically. So a point like R up on the top edge has its partner S on the bottom edge, and that line M cuts the segment between them perfectly in half at a clean 90-degree angle. See? Same rule, different direction. All right, let's switch gears and look at a totally different kind of symmetry. This time, instead of a mirror line, we're going to focus on a single central point. This is called point symmetry, and it's all about rotation, a 180-degree turn to be exact. Let's go back to our trusty rectangle. That point P, sitting right where the diagonals cross, that's its point of symmetry. Now picture a point like M on the top edge. If you draw a straight line from M through P, you'll find its matching point, N, on the opposite side, at the exact same distance from the center. It's just like spinning the whole shape 180 degrees around that center point. And here's the textbook way of saying it. For any point M on the figure, there has to be another point N where P is the exact midpoint of the line that connects them. The key here is that every single point on the shape has to have a partner on the opposite side, exactly the same distance from that central point. So here's a super important difference to remember. While our rectangle had two different lines of symmetry, it only has one single point of symmetry. This is a crucial rule. If a figure has point symmetry, that point is totally unique. There's only one center of rotation. All right, so you've got the rules for line symmetry and point symmetry. Now it's time to put that knowledge to the test. Let's do a quick challenge. Take a good look at these 5 capital letters: M, N, P, S, and X. Think back to that definition we just covered. Which of these letters could you spin 180 degrees around a central point and have it look exactly the same? Give it a shot. Okay, ready for the answers? The letters with point symmetry are N, S, and X. Each of these has a special center point, which you can see marked with a blue dot. If you stuck a pin right there and spun the letter halfway around, it would land perfectly on top of its original outline. M and P, on the other hand, just wouldn't work. So let's zoom out for a second. We've talked about these two types of symmetry, reflection and rotation. What's the big idea that connects them? Well, they're both part of a larger concept in geometry called transformations. So that line symmetry we looked at, that's what we call a reflection. And the point symmetry? That's a 180-degree rotation. Both of these are types of transformations. And the whole point of a transformation is that it moves a figure around without changing its fundamental properties. The shape, the size, the angles, none of that changes. You just end up with what we call a congruent figure, the exact same shape, just in a new spot. And that kind of leaves us with one final cool thought to ponder. How do these simple geometric rules, a flip or a half turn, manage to move and reorient these complex shapes without ever changing what they fundamentally are? It's really the magic of geometry, creating a world filled with these predictable, balanced, and beautiful patterns. Thanks for joining me.